Hello students and welcome to the lecture 2 of Introduction to Mechanical Vibrations. In this lecture we are going to discuss some basic key quantities that are required to understand any vibratory signal. Starting with the first one known as displacement, it is defined as the distance of the vibrating body from its equilibrium position. So it is a distance of the vibrating body from the equilibrium position. Let's say this is the equilibrium position of our spring mass system, and it is displaced from this equilibrium position to some other position, and in this case the spring is compressed. Now whatever the distance is between the equilibrium position and the mean position, as shown here in this case 0.1 meter, this distance is termed as the displacement. In case of linear displacement it is x, in case of angular displacement it will be an angle theta. Okay, now we write t with it to show that it will be different at different time, because the body keeps on vibrating, so your angle will be changing, your displacement will also be changing. Okay, so depending on certain case that you are dealing with. The unit is meter for the linear displacement, it is radian or degree for the angular displacement. Okay, and for example, if a spring mass oscillate between 0.05 and minus 0.05, then displacement varies within this range. So for example, you have a mass spring damper system, you have a mean position that is 0, and then you have two extreme position as 0.05 and minus 0.05. So the body keeps on vibrating within this specific range, and your displacement will keep on changing. However, in each of these cases, the distance of the current distance of the body will be measured from the mean position. For example, if the body is at specific this position, then this will be your displacement x of t. Okay, if the body is, let's say, here, then this will be your displacement x of t, although the sign would represent that in which direction it is, but the value would be measured from the mean position. Okay, now this is the basic quantity number 1, which is displacement. Next is the velocity. It is represented as the first derivative of the displacement, or x dot of t, as shown right here, and defined as the rate of change of displacement with respect to time. Okay, so in this case you have time involved and you have a derivative involved, which is actually taking the first derivative of your displacement with respect to time. Okay, so again in this case it will be defining that what is the velocity of the body at a certain time t. The unit is a meter per second. So in simple harmonic motion, maximum velocity occurs when displacement is 0. So if you are trying to oscillate a body between two extremes, so you have, let's say, 0 position, you have plus maximum position, and then you have minus maximum displacement, and the body is vibrating within these two positions. So there are certain cases, in this case, like one extreme, second extreme, and then you have third, which is mean position. The maximum velocity will occur at the mean position, and at two extreme the velocity becomes 0, the body comes to a stop and then returns. Okay, so it is a simple mass spring damper system. However, I would like to show you this basic simple harmonic motion pendulum. Let me make the damping constant 0, so it is not having damping. We will go into detail of damping later on, but it is a simple harmonic motion pendulum. In this case, the angular displacement, obviously the displacement is angular, so angle is changing, so in this case we are having angular displacement. Let's see, we provide the initial displacement of 25 degree and we release it, so it will start oscillating, and you can see that your displacement is angular in case of degree here, and in the first graph, and at the mean position your displacement becomes 0, and at both extreme position your displacement becomes maximum. But at the same time, if you look at the velocity graph, the angular velocity plot, you would observe that every time the body is at extreme position, the plot or the green line becomes very close to the horizontal line, which means that the velocity becomes 0. And every time the body is in the middle position or the mean position, which was the original position, you have the maximum velocity either in positive direction or in negative direction. Okay, so in positive negative means the direction of the oscillating body. So but the velocity are maximum at the mean position, which is actually this one. This is the mean position that was initially there. Okay, so this is what we mean here, that simple harmonic motion has maximum velocity occurring at the displacement of 0. So when the angular displacement is 0, you get the maximum velocity. When the angular displacement is maximum, you get the 0 velocity. Okay, so that's the what the velocity is, which is the rate of change of displacement. The next third quantity is the amplitude. So we have a vibratory signal. Let's say, for example, we have a sinusoidal vibratory signal. So you have the displacement and time again. So this is time, this is your, let's say, displacement x of t. Okay, and you plot the sinusoidal wave, so it will be something like this. Okay, and it's starting with the amplitude of the displacement of 0, and then it reaches some maximum position and then becomes 0 again, and it reaches some maximum position in negative, becomes 0 again, and it oscillates in this fashion. Okay, now this is when you have time is equal to 0, you have this position, but at a certain point it becomes maximum. Okay, and this maximum displacement is actually what is known as the amplitude. So it is defined as the maximum displacement from the equilibrium position. As in case of this, we had equilibrium position this. So let's say this body is oscillating between these two positions. Okay, so this is, let's say, positive 0.1 and this is negative 0.1. So it is rotating between vibrating between these two positions, and this is your mean position. Okay, so your amplitude would be 0.01. So that will be your amplitude. However, it keeps on oscillating in this specific range. Okay, so displacement can be, let's say, in this position you have a certain displacement of this much. If the body is at this specific position, this will be your displacement, but the amplitude will be the maximum displacement the body can achieve. So the maximum distance from the mean position the body can have is the amplitude. Okay, as we also saw in this graph, we saw that the maximum amplitude that the body can achieve will be our displacement amplitude. Okay, the maximum displacement the body can achieve will be our amplitude. Okay, I hope it is not confusing. If it is, please do let me know in the comments. Next quantity is the time period. Now time period is very simple. If you release the body, let's say I release this pendulum, it goes up to here and then it returns back to its original position. This is known as one complete cycle. Okay, after which it can repeat the same motion. Okay, the time required to complete one full cycle of vibration is known as the time period. Okay, so whatever the time it takes to complete this whole full cycle will be known as the time period. It is its unit is second. Now in case of, for example, if a pendulum takes 2 seconds for one complete swing, so one complete swing means the body goes from here and then returns back to its original position, that's one complete swing. Then if it takes 2 seconds to do that, the time period will be 2 seconds. Simple and straightforward. Now the next is frequency. Frequency is defined as the number of cycles completed per second. Okay, so in 1 second, how many times the body completes this cycles? So it goes from one position to another and returns back to its original position. Okay, in 1 second, how many times it does that? That will be your frequency. So it is number of cycles in 1 second. And if you know the time period, you can actually get the frequency as well. Okay, and it will be its unit is second power minus 1, but it is also known as hertz, Hertz. Okay, and you can just write it, use this unit instead of second power minus 1. If the time period t is equal to 0.5 seconds, then the frequency is 2 hertz. How is that? You just put the 0.5 in this formula and you will get the frequency of 2 hertz, which actually means that in 1 second, every second 2 cycles are completed. The body is able to move back and forth 2 times in every 1 second. Okay, so that is what it means. And the time period of 0.5 second, physically it means that in half cycle it is completing 1 cycle, and in the next half of the second it is able to complete the second cycle. So in 1 second it is totally completing 2 cycles again, which is the frequency. The next quantity is the angular frequency. It is defined as the rate of change of phase angle, and it relates to the frequency as well, the previous one. Okay, so rate of change of phase angle. We have a, let's say, rotating body or change in the angular position. Okay, and we already know that your velocity is displacement over time. So angular displacement over time would give you the angular velocity omega. Now this is also known as angular frequency because it gives you the radians per second. So how much angles are covered in just 1 second. And in this case we were having the cycles per second. However, in angular frequency we have the degrees or radians per second, as you can see right here. If you look at this equation, which is omega is equal to d theta by dt, or angular displacement or time. Now for one complete cycle or one full cycle, you have this angle covered of 360 degree. Okay, and 360 is also equal to 2 pi radians. Okay, if you talk about radians, so in case of 3 degrees it is 360, in case of radians you have 2 pi radians. Okay, so you replace this d theta with 2 pi and dt with the time period, because one complete cycle will mean that you are taking a time period of time. Okay, so whatever the time period is, it will take that much time to complete one cycle. Also, from the previous frequency formula we can see that frequency is equal to 1 divided by t. So this can be rearranged, and instead of 1 divided by t you can simply put this f frequency. So it gives you a relation. So this is why we wrote here that relates to frequency. So this is the relation. If you know the number of cycles per second, you can actually calculate the number of radians per second. Okay, if you know the number of radians per second, if you know this, you can calculate the number of cycles per second. Okay, so they are related, and the equation is given as omega is equal to 2 pi f. Okay, and for example, if you have a frequency of 5 hertz, which means the body is actually completing 5 cycles in just 1 second. Okay, and you want to find out how many radians in 1 second are there, so you can simply use this formula and get the radians per second. Okay, so very important relation, and must be remembered. Now we have the last quantity, which is phase angle, also represented as phi. It is defined as the angle that specifies the initial state of motion at t is equal to 0. So t is equal to 0 is important because we have, let's say this is time, okay, and then you have the displacement, let's say theta of t, or angular displacement for a pendulum. Okay, and this is actually the angle is changing, theta is changing during the oscillation. So what happens is we need to know what is the position of the body, or angular displacement or theta of the body at the initial state. We did move the body to this position and then we release it in order to be able to oscillate. That was the initial displacement that we put in there. So if you look at this, so we had to give it some initial displacement, for example 21 degrees or whatever, and then you release it. Afterwards it actually started oscillation. If it was at the initial position and you release it, there will be no displacement because the body stays at that specific position. Okay, now it is very important if you are using, for example, a sinusoidal oscillation like in this case, then you need to know what is the initial displacement of the body, initial position of the body. So if it is sinusoidal, it will be something like this. Okay, but it is very possible that at t is equal to 0, it is not at this position. Okay, it may be at let's say the extreme position at t is equal to 0, like for example in our case that we give. Okay, so at initial case we put a certain displacement theta, we gave a 21 degree of displacement, initial displacement. So that is actually this 21 degree is our phase. Okay, now for this signal we have the theta of t is equal to the amplitude sine theta. So this is the equation for this red signal. Okay, but when you are starting from a different position, okay, then you have to add this theta of t will be modified as a sine of theta plus phi, this additional displacement that you have added. Okay, this phi that you have added will be added to the angle. Okay, now we know that the theta is the angular displacement. Okay, and we also know that the angular velocity will be equal to the displacement over time. Okay, and then theta can be modified as omega t by multiplying t over here, and that is why we simply mention this theta as omega t and then plus 5. Okay, this will be in case of if you are talking about theta of t or angular displacement. Okay, it can also be in case of linear displacement x of t. We will discuss that in later on, because both are simple harmonic, whether it is pendulum or it is the mass spring system. They are having, if they are having simple harmonic motion, then they will have the same pattern. Now if phi is equal to, let's say, 0, motion starts at equilibrium, like for example in case of the red signal. If let's say the phi is pi by 2, okay, so if you have a phi pi by 2, instead if this is 0, it will become the same previous signal which is for the red signal. If the phi is not 0 and is pi by 2, then it will start at the maximum displacement. Okay, so this, whatever the initial position of the body is at, which means that time is equal to 0, that will be our phase angle. Okay, I hope it is clear enough. Thank you very much and take care. Goodbye. See you in the next lecture.